cast iron pans right out there on the stove. They're kind of too heavy for shelves, so I just leave them out there on the stove all the time.
Yeah, we also had a discussion about sharp implements and knives that I'll get into in the talk too. Jen and I share a love for cast iron pans and high quality cutlery.
We do.
So that'll be in the main body of the talk.
Cast iron is just as good as Teflon. It's just that it's heavy, and of course nobody would even think of putting something like that in the dishwasher because it would probably bend the dishwasher because it's it's like ridiculously big and large. So they tend to keep their nice patina, and then I can cook in it. I could flip an egg if I could move that cast iron pan fast enough because it doesn't stick, but it's too heavy to really flip an egg. I'm curious about how big the audience is going to be tonight because it is Halloween.
It is Halloween. On the East Coast, it's probably going to be rough.
Yeah. Well, it's Halloween, but people can leave their Husky Bites on as they run and answer the doorbell. All right, so I don't have much by way of slides to share, but I'm going to find that page and get ready. It's funny, we're both in hotel rooms.
It is funny.
Yeah, no, I did not organize an alumni reunion in this area because this is mostly a personal trip. But all right, we are being live streamed. So welcome to Husky Bites. If you're just joining us on Facebook, and I'm going to share my slides. No, that's not what I want to do. First, I want to, you'd think I do this often enough. I want to share screen. And then this is what I want to present. I did it. Phew. All right, we'll just give it a few more minutes because there's a bunch of people that joined us right on the hour. But it's hilarious because usually I do a weather report, but I have no idea what the weather's doing in Houghton because I'm in Chicago. In Chicago, it's a little bit overcast and pretty warm.
It's very windy in Richland, Washington.
You got wind out there? Okay.
Very windy.
Yeah, it's a beautiful part of the world. How long are you out there, Walt?
I'll be back Wednesday.
Okay. I'm not sure when I'll be back. Either Friday or Saturday or Sunday, one of those days. So I've told you this story before, but I'll relay it one more time. So they ended up, when I became a faculty member at Georgia Tech, I guess that was 3 years after you left, and they gave me that lab, but nobody had cleared out the drawers and things like that. And I remember seeing sample after sample after sample that said Milligan on them. So I am responsible for recycling or whatever I did with them, all your metallurgical samples, and I hope you never needed them again.
Well, the ones that I needed, I brought with me. So
there you go. What were you working on in those days?
I was working on creep and fatigue of nickel-based superalloys for aircraft engines and for space shuttle main engine.
So what particular alloy were you working on? Or
I was working on single crystal superalloys mainly.
Okay.
Cast turbine blades.
So nicocryles?
Sort of, yeah.
Okay. And so you were doing these at temperature then?
Yeah.
What kinds of creep temperatures were you looking at?
Up to 1100 degrees C.
Okay. And was Intelovich your advisor?
He was.
Okay. And he left just as I got there. And he went west somewhere. I'm trying to remember where. Was it Washington State or something like that?
That's where he went.
Okay. Yeah, I lost track of him after that. But yeah, no, he hired me, and then we had an interim chair, and then we had an actual chair. And so I had 3 chairs within my first year. All right, well, let's get started. So welcome, everybody. You are joining us for Husky Bites. I'm very glad to have you join us. My name is Janet Callahan. I am Dean of the College of Engineering and the host. Husky Bites are a free Zoom webinar series and we are in season 6 of Husky Bites, and the objective is to have some fun and learn something new. So this is our fall menu. As you can see, we're kind of more than halfway through the series. Tonight, we're going to be hearing from Walt Milligan, and we'll hear more about that in a second. So we have 3 left. And so up next is going to be John Vucetich, who is one of the distinguished professors here at Michigan Tech out of the College of Forest Resources and Environmental Sciences. And co-host with that is going to be Becky Castle, who is someone I met through Husky Bites, who is a teacher in Pennsylvania who uses the book he wrote in one of her classes. And her daughter actually attends Michigan Tech here. Her daughter is the granddaughter of one of our alumni. So I'll look forward to seeing you guys next week. So I'm going to stop sharing and you can go ahead and share your screen, Walt. And I'm going to introduce Walt. So Walt Milligan earned interesting degrees, and I just wrote this down and it just fell out of my brain. So you earned your bachelor's degree in metallurgical engineering from the University of Cincinnati, and then your master's and PhD both from Georgia Tech. And we almost overlapped there because I arrived at Georgia Tech in '92 and he left Georgia Tech in '89 when he came to Michigan Tech to become a faculty member in the Department of Materials Science and Engineering, where he now serves as chair of the department. And he's been chair since 2021. You're a fellow of the ASM. You are a distinguished life member of Alpha Sigma Mu. Your father was also a metallurgist in a way. He worked in the forging industry as a machinist. And another interesting thing about Walt is that he has 2 sons, both of which are also metallurgists. And then a fun fact about Walt is that he loves to play hockey. His whole family likes to play hockey, and the position he plays is goalie. So with that, Walt, are you sharing screen?
I think I am. Can you see my screen?
I can see your screen. It's not maximized, though.
No, I'm going to maximize the slide presentation in a minute.
Okay.
So
all right, I'm going to turn it over to you and take it from here.
You can see the website with the video playing, I hope.
Yes, we're seeing a very sharp knife cutting up things.
So after this seminar was announced, I got an email from a former student who's on the call. I saw his name, Tristan Kolb, and he works for an outfit called the New West Knife Works out west, Jackson Hole and other places, and they've got a really nice website here. We're going to talk a little bit more about their knives later, but it's an American manufacturer of very high quality knives. And one thing we're going to talk about today is knife technology and how do we harden them and what makes a good knife and things like that. So thanks to Tristan for getting in contact with us, and you can see some of their stuff there. It turns out that this place was founded by a fellow called Corey Milligan, and I don't think
any relative.
I don't think it's a relative, but they've been in business for about 25 years. And Corey Milligan is their founder. And if you take a look at their website, which is newwestknifeworks.com, you'll see they make some really beautiful handmade knives that are pretty pricey. $400 for a shot.
I just bought myself one of those, the 7-inch Teton Edge Sentoku, I think that's the one I bought.
Yeah, I got a picture of it later. So anyhow, so that's introducing things. And so if I say something really stupid here, because knives are not my specialty, then Tristan can chime in the chat and let me know what I said wrong. So I'll get my slideshow here and we'll get started.
And so audience participates, you can ask questions using the Q&A feature. The chat is disabled. So that's how you can communicate, and just ask questions all along the way and we'll answer them all at the end.
Okay, so thanks for coming, and we'll hop right into it. So, oops. I'm going to talk about a few things, and I'm going to speak as if people on the other end never took an intro to material science class. So I'll start with some of the basic stuff, but I will have to get into a little bit of science so that we can understand a little bit about how these things work. So first of all, I'll talk about some everyday examples, as was talked about in the publicity for the talk. I'll talk about the concept of hardness and how we measure it. I'm going to talk about phases in structural metals, and then we're going to have to get into some phase diagrams so that we can understand heat treatment. And then I will talk about hardenable knives or hardenable steels for knives and other things. And then non-hardenable stainless steels for flatware, for example, knives and spoons and forks that you might get a couple for a wedding gift or something like that. And we were going to talk about cast iron pans, but I ended up with too much material, and I'm hoping that I don't take too long. So if you ever go shopping for high quality steel products, you'll see the word tempered a lot. And so I just have some examples here. This is an ice scraper, and it says forged and tempered. You might have noticed on the video that was playing on the New West Knife Works that there was some forging going on there. They put some steel blocks into a furnace and got it red hot and then smashed it into shape, and it ended up being a knife. So one example here is this scraper. Here's an example off of Amazon. It's a pretty expensive shovel, tempered steel. It's $50 instead of $12. And so the tempering is going to be a heat treatment process that we'll explain in detail today. Here's another example, utility knife for box cutter, also tempered and hardened. Final example, here's an inexpensive knife that you might find at Walmart. And even those kind of knives, if you come down here and take a look, I'm going to activate my pen here so I can annotate. Down here, you can see that it's hardened, tempered steel. And so I want to explain what that all means in this talk today. I don't know how many people have seen the show on TV on the History Channel called Forged in Fire. They have a contest where they try to make swords usually, or knives or something of a certain design, and the contestants have to go back to their garage and wherever they live and come back with their knives later. And here's an example of a kid that tried to make a sword. And so this is going to describe the process, one of the processes in the heat treatment step called quenching. And so I've got to figure out how I can make that video play in full screen mode. It played when I tried it before. There we go. I don't have any audio on this. I just took the video off of the YouTube channel. So he's smashing the sword into shape. He's got it red hot. And then after he smashed it into the rough shape that he wants, he's going to put it in the oven and he's going to get it glowing red hot. And then he's going to take it out and he's going to dump it in a fluid. You can see that safety is not his strong suit. So anyhow, the question is, why do we do that? Why did he have to take that knife or the sword that he had forged and put it back in the furnace and then quench it? And that's one of the key aspects of making a sharp knife. And so we'll get into that. Here's another example of a hardened steel device. I don't know how many people have heard about this, but there's a device called a hori-hori, which is a Japanese name. And it's basically a sharpened garden trowel that was developed for planting bulbs and cutting roots and things like that in Japan. You can see that it's got a scale on it. So if you want to put your bulb to a certain depth, you can actually measure it with that. And this particular thing has a serrated edge down here for doing some cutting, and it's got a very sharp edge up here. And so this is also going to be heat treated in the same kind of a way. You can see it's got some curvature to it. One of the reasons that I'm doing this talk is because Janet and I were talking about this. I got this from my wife, and she likes to do gardening, and Janet loves to do gardening. You should see the front yard of her house. It's beautiful. She's out there all the time. And so she liked this so much that she bought one for herself. And we'll have another story about that later. This is the front of the case on the hori-hori that I bought. You can buy these for $12 on Amazon and probably at Walmart, or you can spend $60 like I did. And when you spend $60, you get a high-end stainless steel. I'll explain that composition a little bit later. And you can see down here, it says full quenching. And I'll explain the full part, which is a little bit more in depth than you might guess. And it tells you what the hardness is up here. And I'm going to explain what hardness means in a bit. So this particular thing is heat treated to a hardness of Rockwell C58, which is not super high for a high quality chef knife, but it is very, very high for a garden trowel. So what exactly is hardness? People have probably heard the term. Hardness has a specific meaning for metals, and basically it's tested by this benchtop device over here on the left. Every materials department and every factory that makes these kind of things has many of these in place. They're not very expensive, but they're on a benchtop. And what they do is they take an indenter, and the shape and the material that the indenter is made out of depend on how hard the metal is. And I'll play this video, hopefully. it's not letting me use the pen and the video at the same time. So I apologize for going in and out. So
In
that,
modern testing machines, the Rockwell hardness test is fully or
yeah, we don't need the video on this, but basically it's going to take that diamond tip indenter there and it's going to go down and it's going to make an indentation in the metal. I don't know if you can see it going up or down, and then the machine automatically detects the depth of the indentation, and the deeper it goes, the softer the metal is, and it displays the hardness on the screen. It's a very rapid test. You can do this in 30 or 40 seconds. It's non-destructive, so you can actually test your part and then put it in service in some cases. And this is the standard way that we measure the performance of things like knife steels. Most knife steels are going to have the Rockwell C scale, which is what we showed on the Hori Hori. And that is what that means is that the indenter is a diamond tip and 150 kilogram load, and it's reported as a hardness of HRC, or sometimes the symbol capital R subscript C for Rockwell C. And so if you go to the New West Knife Works website, they claim that they can get hardnesses of 77 on their knives. That's pretty impressive. If so, I don't see any reason why it wouldn't be, but a very high value for a hardness for a good quality kitchen knife would be 65 or 67 Rockwell C. So we're going to need to talk about phases so that we can understand why we're doing quenching and tempering. And so I'm going to introduce the concept here of a phase diagram. This is a simple phase diagram for water. And what it's going to do is it's going to plot on the x-axis, it's going to plot the temperature, and on the y-axis, it's going to plot the pressure. And at its simplest, the phase diagram tells you what phases are stable at the combination of variables in question. So for example, at 1 atmosphere pressure, which is just regular room temperature conditions, and at 20 degrees C or so, which is room temperature, you would come up and plot that point there, and you would be able to read that the stable phase is liquid at that combination of temperature and pressure. If you keep the pressure the same and change the temperature, you can see where water boils, it's 100 degrees C. You can see where it freezes, it's 0 degrees C, for example. And you can also change the pressure and figure out what phases are stable. Here's a picture of a couple of rocks I found on the beach at McLean State Park. And the reason I'm showing these is because you can see with your naked eye that if you look at either one of these rocks, they don't have a homogeneous and uniform color. The one on the left has some white stuff and some black stuff. The one on the right has 3 or 4 different colors. And it turns out that these rocks, because those colors are different, those are actually different phases. And these phases are going to have different chemical compositions and different crystal structures. And so it's going to turn out that structural metals are going to have exactly the same thing as we showed on the rocks there. That high performance structural materials are going to be made out of materials that are more than one phase. And I almost didn't put this in, but I decided to put it in. And again, I apologize for having to get out of here. But basically, all metals are crystalline in nature. And so this is showing a kind of a cartoon of a very simple crystal structure. And it turns out that when you want to decide when a metal is going to deform, when it's going to lose its shape, for example, when a sharp edged knife might get dull because it's going to go from sharp to mashed out. The reason that happens is because a defect in the crystal called a dislocation moves. And if you watch how that red line moves through this crystal, what you'll see is at the end, we had a crystal that started out as a cube, and now it ends up looking like it's got an offset there. And if you did that on multiple parallel planes, you could actually get enough deformation that you could measure. And so, for example, if you've got a knife, a chef knife, and it's nice and sharp, and then you cut into a bone or hit your cutting board a little bit too hard and it gets dull, what's happened is that billions of these defects have moved. And basically that's why it changed the shape from sharp to dull. And the point here is if I can take something in the microstructure and put it in the way of this thing moving, we can increase the strength. So that's why high performance metals all have 2 phases, because the second phase can get in the way of this dislocation moving. And when it does that, it increases the strength of the material.
I'm proud of you for using the dislocation word, Walt.
Thank you, Janet. I almost didn't do it. So anyhow, here is an example of 2 different materials. The one on the upper right here it's a microstructure. I can't get into how we make this, but it's a picture of the microstructure of pure iron. And the only thing we see are these black lines, and these are grain boundaries. So metals have grains just like wood does. And each one of those individual round blobs here is a crystal that has a given orientation, and the interfaces between them are the grain boundaries, but there's no second phase in there. And so because of that, it has a very low strength. I can't get into the details of what a yield strength is, but basically this is, if you bend a coat hanger, for example, if you bend it a little bit, it'll snap back to its original shape. If you bend it too much, it will be permanently shape changed. And so that is a measure of the so-called strength. 25 megapascals for pure iron. If I take iron and throw some carbon in there, and so these two steels down here have 0.8% carbon. This is the composition of piano wire. And the interesting thing about these two materials is that in both cases, we took the material and heated it up red hot, just like the person on the Forge of Fires and just like the people at New West Knife Works. So we heated it up to red hot, and then the difference between the two is the cooling rate. This one was cooled relatively slowly. This one was cooled much more quickly and then tempered. So it was quenched in oil or in water and then tempered, and I'll explain what tempering is later. And you can see that even though these two materials have the exact same chemical composition and they were heated to the exact same temperature, when we change the cooling rate, the strength is different by a factor of 5 or so. And so the point of this is that it's not just the chemical composition that determines the performance of your steel. It's also the processing which affects the microstructure. So this is going to be probably a little bit too much detail for people who aren't technical, but we need to get into it anyhow. This is the iron carbon phase diagram. And in this case, we are not plotting temperature and pressure. Instead, we're plotting composition on the bottom axis here and temperature on the y-axis here. And I just had an issue there, sorry. I have a annotation tablet that was acting up there. So basically this, just like in the case of the water phase diagram, is a diagram that explains what phases are stable at a combination of temperature and composition. So most steels have carbon concentrations less than about 1% by weight. And so if I take a look in this region down here, I have a two-phase mixture of a phase that we're going to call alpha, which has this crystal structure here. It's an ordered crystal, just like ice crystals are. And that's called the body-centered cubic crystal structure. And it also has a carbide in there. That's that iron carbide. And that carbide is this line over here. If you take a look up here on the atomic percent scale, that's 25% carbon. So it's three irons and one carbon, Fe3C. And so this is going to be able to give us two phases, and that iron carbide phase is going to be able to strengthen the material. If I go back and look at this picture back here, these white blobs in here are the iron carbide particles. And over here, these worm-like features are. This one is a much higher magnification in an electron microscope. And so these carbide particles are much finer and much closer together than they are over on the right, which is one reason that it's harder. Basically, the harder you want your steel to be, the smaller you want the carbide particles, so they're more numerous and closer together, so that they can inhibit the motion of dislocations, and that increases the yield strength. Now, here's the magic about steel, and it's a unique material, and people don't understand how magic this is. If I take a steel that has 1% carbon in it, for example, right here, and I'm down at 400 degrees C or lower, I have a two-phase mixture of alpha plus Fe3C. If I heat it up to above this red line here, iron is a strange material. And what it does is it changes its crystal structure. If you have pure iron, that happens at 912 degrees C. If I have this alloy here, it happens at this temperature here. But once I get up here, now I have a single phase material. The carbides have been dissolved. The carbon is evenly distributed in solid solution, so it's nice and uniform and homogeneous. The crystal structure has changed to face-centered cubic. And the good thing about this is if you can do that, if you can heat the material up to that temperature, you can dissolve whatever garbage you had there before from the steel mill or whatever. And now you have complete control over what the microstructure is by controlling the cooling rate. So once again, we can take a material that's two phases at room temperature, and we want to control the size and the shape and the distribution of that second phase. The way we do that is we heat it up in the furnace, and then we control the cooling. So the Forge of Fires guy, he put it in the furnace. The New West Knife Works guys put it in the furnace. And the reason they do that is to change whatever we had down here into a single phase, and then we can try to figure out how to control it. It turns out the difference between these two phases is not just crystal structure, but also the austenite phase, which is at high temperatures, is not magnetic. And the ferrite, which is at lower temperatures, is magnetic. So why do we heat the steel to austenite and then quench? So I explained on the last slide that if we heat it up to the austenite phase, that we can dissolve the carbides and get a fresh start with our microstructure. It turns out that for maximum hardness, we want to have, as I said before, we want to have the smallest, most closely spaced carbide particles possible. And we can do that if we quench the material very, very quickly from austenite. And the reason that that works is we form a new phase called martensite that doesn't show up on the phase diagram because it's not an equilibrium phase. So we're going to quench the material from red hot in water or oil. And when we do that, we're going to transform the austenite into a new phase called martensite. I'm going to show you some videos. Maybe I can do this without getting out of here if I do that. Yeah, I see. Sorry about this again. So this is a device that we have in our lab for demonstrating heat treatment. And those of you that were at Michigan Tech before about 1993 will recognize the old MTU logo there on the upper left-hand side there. And what this device is it's like a light bulb. We have two electrodes here, and we have a wire in the middle, and we can heat it up by just running current through there. And so you can see right now that this steel wire that I have in there, and this is piano wire, has been heated up. It's red hot. And what I'm going to do is I'm going to quench it. And I'm not going to quench it by dumping it in water because it's a wire. What I'm going to do instead is I'm going to take a wet paper towel. I'm going to turn the power off, and then I'm going to quench it in that order. So I'll play that again. It's red hot wire. I turn the power off so I don't electrocute myself, and I just hit it with a wet paper towel really quickly. And so that is a quenching operation. And then I'm going to show you in the next video what the properties of that material are. Turn the sound off again. So I'm going to take the wire off of there. It's incredibly brittle. It's like glass. If you would have done anything else to that wire, you could have tied it into a knot. And so this martensite phase that we form is absolutely useless. The reason that we form it is because it's an intermediate step in order to form the microstructure that we want at the end. So let's get into that next. So why do we want to make useless martensite? The reason is we can take that martensite and reheat it to an intermediate temperature. And these temperatures are typically around 200 or 300 degrees C, the kind that you could get in your home oven, like a pizza baking temperature. And what happens is the martensite transforms to the stable phases of ferrite and carbide. And that final step is called tempering. So it's kind of like the steel was in a bad mood, so we had to temper it. I think that's where it came from, just shop jargon from 200 years ago or whatever. And so when you see these products online or at the store and they say tempered, what they mean is that we had a 3-step process. We heated it up red hot to austenite, and then we quenched it, and we formed a really useless brittle phase. And then we reheated it a little bit and tempered it. And when we do that, we can have a very, very high hardness, and we can have very, very fine carbides, many of them that are very close together. And so we can get a very high hardness and a very high strength. And the amazing thing about these steels is they also have unbelievably high ductility and fracture toughness. And so that's one reason why these are so useful, not only in knives and things like that and in hori-horis, but also in a lot of engineering materials and components. The way you control the properties after the quenching step is by controlling the temperature and the time of the tempering. And so this plot here shows a tempering curve. And on the left-hand side, we have hardness, again in Rockwell C. And on the x-axis, we have time in the furnace. This is the same steel that I showed you that we did the quenching on. So this is piano wire. And so, for example, you can pick whatever temperature you want and then pick the time if you have the data for your steel. And so, for example, if I wanted to take this steel and temper it at 200 degrees C for about an hour, it should have a hardness of about Rockwell C62, which is harder than the hori-hori. And it's also a pretty good hardness for a plain carbon steel like this. As you increase the time or the temperature, the carbides grow more quickly, and so the hardness goes down. It's not always a bad thing. For the hori-hori, for example, which is not made out of this steel, we'll get into that in a minute, but it turns out that the hardness is about Rockwell C58, so it's not going to be as strong as it is here, but it's probably going to be tougher and more ductile and easier to form and it might not be it might not be so prone to chipping in a very sharp edge. So once again, the 3 steps that we have to do here are we have to heat it up to the high temperature austenite. We quench it to form martensite, and then after we form the martensite, we got to get rid of it. And so we temper it for an amount of time, and the result of that microstructure is called tempered martensite, even though there's no martensite there. And that drives students crazy in the intro class that I teach, because it's called tempered martensite and there's no martensite there. We called it tempered martensite because that's how we made it. I also note over here that if you're doing industrial operations, there's a very, very weak dependence on time. So if you go from 1 hour to 2 hours, the hardness only changes a very little bit. And so that's a good thing if you're doing quality control, because you don't want you don't want your thing to get too soft if they left it in the furnace for a little bit too long. So now let's talk about the real stuff. Let's talk about the stainless steels that those $400 knives are made out of. Piano wire is fine, but the products we're interested in today are stainless steels. So the definition of a stainless steel is an alloy that contains iron and chromium. The reason they're stainless is because the chromium oxidizes on the surface and it forms a protective coating. And that coating keeps further oxygen from going into the material and oxidizing it, turning it into rust, or doing other bad things to it. So all stainless steels have chromium in there. Some have carbon intentionally. We'll talk about that. Some require very low carbon. I'll talk a little bit about that. Some have nickel, and there's about, I don't know how many thousands of different kinds of stainless steels, but we'll talk about some examples of the most common kind. So there are 3 basic classes. We can have martensitic stainless steels, and they are hardenable, just like we showed in the carbon steels. And the process is exactly the same. We have to austenitize and then quench and then temper. The carbides that we get are different. They're not Fe3C. I'll talk about that in a bit. But these are hardenable and very high performance for knives and shovels and horis and things like that. We can have ferritic steels that are not hardenable. They're much more low cost and much more affordable, moderate corrosion resistance. And we can also have austenitic stainless steels, which are more costly and much more corrosion resistant. So we'll talk about the martensitic stainless steels first. So the most common one that you'll come across if you work with these things is a steel called 440C. If you try to buy something online and they call it surgical stainless steel, this is usually what they mean. So you can see the composition up here. This has 18% chromium. That means it's much more expensive than plain carbon steels because chromium is expensive. It's got pretty high carbon. It's got more than the 0.8%, and it's got a little molybdenum in there for heat treating purposes. And we do the same processes to this. We austenitize it, we quench it and temper it. It's strengthened by basically Cr23C6. It's not just chrome, but it mainly is. And so we can get very high performance by doing that. So once again, there's the hori, and we got 58 Rockwell C, they claim on the label there. And when I first bought this, I thought to myself, full quenching, what the heck does that mean? What would a partial quench mean? And so I dug into this steel, and this steel that they're using here is basically 440C, and they've added a little bit of something else, I think vanadium or something, to get some other carbides in there. And so the steps that are necessary in this knife steel, and probably in the knife steel that New West uses, I'm assuming, are we have to austenitize and quench to get martensite. But then, because of the composition of the steel, we don't get rid of all the austenite if we just stop at room temperature. And so that austenite that stays in there will not temper, and it will end up being a soft phase in there, and it will hurt the performance. And so when they say full quench on this thing, what they mean is they actually had to cryo quench it. They had to put it in liquid nitrogen or in a bath of dry ice or something like that, depending on the temperature, to get rid of all the retained austenite. And then they temper it. And if you don't do that step, the cryo quench step, you're only going to get 52 Rockwell C, because the retained austenite is going to be a soft phase in there, and you're not going to get the full benefit of the material composition. This is a picture of my new hori, and I think if you read the thing there, I think you can tell that the Japanese manufacturers maybe need some help with their translation of English there. The specialty knife of function blade. Don't know what that means, but I can tell you this serrated edge is very, very sharp, and this straight edge is incredibly sharp. 58, like I said, it's not sharp for a chef knife, but for a garden trowel, it's incredibly sharp. And in fact, this is a picture of Janet's hori that she bought after she learned about the one that I got my wife. You you can actually see that it's gotten a lot of use. There's a lot of scratches on there. And Janet was digging in the garden one day, and she was using two hands, and she actually almost cut her finger off. And so she got mad at it, and she took that knife and rubbed it up against a brick to get that sharp edge to be a little bit less sharp, so she wouldn't cut her finger off. And so,
And it's still pretty sharp. I'm just saying,
Yeah.
it's not so sharp that just touching it cuts you now.
yeah, so 58 Rockwell C is not bad for a garden trowel, or even for a kitchen knife. It's not too bad. And it's also relatively stainless. You can see there's a little bit of staining on there, but it's a really cool tool. I really like it. Like I said, Janet does a lot of gardening. It's what she does a lot in the summer. Back to our friends at New West Knife Steel. Here are 3 different steels that are used for high performance kitchen knives. The one on the top is the one that they use for those $400 knives. This is, I don't have time to get into the details of this, but it's a powder metallurgy alloy that was developed by Crucible. It's got very high carbon, 1.4%. It's got 14 chrome, and vanadium and niobium are in there because they form different carbides besides CR23C6. And these vanadium and niobium carbides end up being very, very fine from the quenching and the tempering, and they can give very, very high hardness. And as I said, they claim on their website that they can get up well over 70 Rockwell C for those knives, and they still have good toughness. It turns out that 2% molybdenum helps a bit with the toughness, for reasons that I don't have time to get into. Shun is a very expensive Japanese knife. They make a lot of Santoku knives. And you can see similar, they've got a very high carbon, about the same chrome, but they don't have as much of these hardening phases over here, so it's not going to be quite as hard. And then, of course, a very common knife, if you are in the kitchen area, is Wusthof, which is made in Germany. I have a set of Wusthof knives that I'll talk about in a minute. Much less carbon and none of this other stuff. And so this is not going to be nearly as hard as that one. But the advantage of that is that if you are not an expert sharpener, this knife, which I own, and I'll talk about in a minute, is much easier to sharpen. Whereas this one is so hard that you almost have to be a professional. And in fact, these guys actually have a lifetime deal where when your New West knife gets dull, you can mail it to them and they will sharpen it for you. Because if you're at 70 or 72 Rockwell C, that's going to be really, really hard for an amateur to sharpen. So this is a combination of good sharpness. It'll get dull quicker, but it's pretty sharp when you do it, and you can do it with one of those knife sharpening devices that you can actually just buy in the store. So a quick word about storing your knives. Hard, sharp edges can chip, and so don't throw them in the drawer. I think most people know that. Here's how Janet stores her knives. She has a magnetic thing on the side of her cupboard. Here's how I store mine. I've got these plastic knife guards. These are 3 Wusthof knives. This one is a serrated bread knife that also is really good for slicing tomatoes. This is a paring knife, and this is an 8-inch chef knife. I think I've used this chef knife every single day for the last 10 years, and it's just held up great. And maybe I'm going to buy a New West knife after I saw what these guys make, because it looks pretty spiffy. But this has been a great knife, and sharpen it every once in a while, once a month, every month or two, and it does a really good job. So that looks like a really nice set, but I don't know if I'm going to be laying out $2,700 for a set of knives or not. Janet just bought one of these. It's a picture from the website because she's in Chicago, and even if it got here on time, she is not.
No, it was delivered. I took this before I left.
Oh, you got your knife.
Mm-hmm. That's
so it came with a leather sheath, I guess, right? Is that a leather sheath for it?
Yep, it did.
Yeah, so that's my approach here, except it's pretty leather instead of cheap plastic. So that came pretty quickly then.
It sure did.
I'm almost done. I know I'm going over time here, but I've got about 5 more minutes, I think. So the class of knives that I've just talked about were able to be heat treated and hardened to very high hardness for very sharp edges, but you don't always want that. Sometimes you want something else. And so the other 2 classes of stainless steels, the first one is ferritic. And so this one is relatively low cost. You can't heat treat it. You can stamp it or forge it, and you can get some benefit of strengthening by work hardening it, but it can't be heat treated. The typical ferritic stainless steel is 409. The only thing it has is 11 carbon or 11 chrome in it. So it's 89 iron, 11 chrome. It has reasonable corrosion resistance, and so inexpensive cutlery you might buy at Walmart, for example. And one of the big One of the big advances in mufflers and tailpipes, I'm old enough to remember cars from the 70s where you had to get a new muffler and a new tailpipe about every year and a half because they turn into a pile of rust. And they started making those out of 409, and now they'll last 10 or 12 years. So they have pretty good oxidation resistance. They're also good if you need to weld something because you can weld them. The martensitic steels, you have trouble welding because of the heat treatment issues after that. They have moderate corrosion resistance. And so they have the body-centered cubic structure, which is the ferrite phase in the phase diagram. I'll show that diagram in a second again, and they're very magnetic. The austenitic stainless steels are interesting. And so what the austenitic stainless steels are is if you can add nickel to your steel, then you can take this austenite phase here, which is not stable below 727 degrees C for a plain carbon steel. And the 727 degrees C, that would be glowing red hot in the furnace, starting to glow red hot anyhow. And so if you went below that, the austenite is no longer stable. However, if you add nickel and chromium, you can stabilize the austenite phase so that it's actually stable at room temperature and below. And so that's what these steels are going to be. They're going to have chrome and nickel in there. The most common steel that people know about that's austenitic is called 304. Again, it can't be heat treated. It's got 18 chrome and 8 nickel. This is a very expensive material compared to other steels because chrome and nickel are both expensive. And in this particular case, you want to have very low carbon because if you have carbon in these steels, they tend to form a chromium carbide phase at the grain boundaries, and that ends up giving you a corrosion problem. So for example, if you're using this for a plumbing fixture, you can actually get pinhole leaks in your plumbing fixtures because of corrosion if you have carbides in there. So typically we want to have chrome and nickel and very low carbon. And this is useful for expensive cutlery like knives and forks and spoons. It's the most common material for plumbing fixtures. If you go to Burger King or something, you see the shiny stainless steel countertops, they're all made out of this. It's also biocompatible, so there are some implant materials that are made out of this. And once again, this is the face center cubic phase, which is austenite, and it's not magnetic. And so that's the third class of steels. And now I'm going to have to, oh, it's going to let me do it this time because I didn't turn my, I guess I will have I'll have the sound on this one. I didn't turn my pen on. That's why it's going to let me do this. So here's a demo that I filmed a couple of days ago about these knives or forks.
Okay, so to demonstrate the crystal structure that occurs in flatware that you can buy at the store, I've got in front of me, I've got a magnet underneath the Michigan Tech pin there that you can see in the front. And then I have 3 different forks, and we're going to see how they behave when they come in contact with this magnet. So the front one is one that I paid $1.49 for at Walmart, and I have it at my office. And it doesn't get put in a dishwasher. It doesn't get very much use. It doesn't have to look pretty. So I'm perfectly willing to pay $1.49 for it. And if I take that fork and if I put it anywhere near the magnet, you can see that it actually flew up and attached itself very, very rapidly. So once again, if I put the fork anywhere near it, it's going to fly up. And the reason for that is that this is a body-centered cubic stainless steel, probably 409 or 430 or something like that. A little bit of chrome, no nickel, fairly corrosion resistant, and very much less expensive. Second one here is one that I think I got as a gift in a set. And so this one is much more expensive. And if I put that fork near there, it doesn't fly up until it gets very close to it. And then you can see that it also, even though it is somewhat magnetic, it isn't nearly as strongly magnetic as the other one. And so it kind of grabs on, but not really. Much less magnetic. And in fact, you can put this through a demagnetization operation if you wanted to take the magnetism almost completely out. And that's one thing that they do in industrial operations where they sell stainless steels, austenitic stainless steels. Here's the most interesting one. This is a fork that my wife and I got as a gift a number of years ago in a set. It looks pretty fancy, and it was, I think, pretty expensive. And so you would think that it would also be face center cubic austenitic stainless steel. And it turns out that that's not the case. And this is really interesting. I didn't really learn this until I made this video today and got a whole bunch of forks out of my drawer. But this fork, which was probably pretty expensive, actually is ferritic. It's body-centered cubic. it's highly magnetic. And maybe that explains why, if you take a look at this thing, you can see the stain on there from the dishwasher. We've always kind of been mad at this set because the dishwasher ends up staining the fork. You can see that kind of orange stain there, and there's another one on the back that isn't showing up very well. And my wife blames our water or our dishwasher, but really, it turns out the steel's cheap.
So anyhow, the reason that it stains is not because it's magnetic. It's not because it's body centered cubic. It's because it has less chromium and no nickel in there. So that's if you buy high quality cutlery at some place besides Walmart or Target, then it's going to be 18 chromate nickel probably, and that's why it's not going to stain in the dishwasher like that one did. So I think that's all I have, and I went a little bit longer than I wanted to, but I'll be happy to answer any questions.
Super. All right. So Walt, click on the Q&A feature and you're going to see a whole bunch of questions, and you can take them in any order. While you're picking out a question to answer, I'm going to tell you that when you showed me that little video, I immediately went home and tried my own fancy forks and knives and spoons, and they are not magnetic. So I feel justified in having spent so much money per place setting on mine.
Good.
All right, go ahead.
I'm looking at my feed here. Are all cast iron skillets made of gray cast iron? I think so. I'm not a cast iron expert, but we make cast iron skillets in our foundry, and they are gray iron. It's got very good thermal conductivity and very good damping properties, and it's easy to cast. So yeah, I think they're all gray cast iron. Not totally sure, but I think they are.
And I do not use induction cooking, Larry. Do you, Walt?
I don't.
Yeah, I use a gas flame.
So Walt Lang says that every metallurgist has an affinity for good knives. Whenever my wife and I go shopping and we're looking at knives, she wants the clerk. She tells the clerk, warns the clerk that he's a metallurgist. Walt got his PhD in a metallurgical topic and then went off and became an electronic materials vice president at IBM eventually. Ward Christensen says he just turned 77. The West Bend company at which I worked has an interesting hybrid, a stainless steel skillet with a cast aluminum bottom. Yep. There are lots of pans and pots like that have a good heat transfer coating on the bottom, or even a bimetal one, sometimes copper and sometimes aluminum. And
stainless steel is not that great a conductor, it turns out. So that's often why you get copper bottom pans and things like that.
So Janet, there's a question for you about toxins.
Uh-oh. Read it.
Dean Force says, cast iron is better than nonstick coatings regarding toxins. Well, don't miss Lake Chelan. Great wine there. I'm going to write that one down. Lake Chelan. Okay. My son and I are probably going to go to a winery tomorrow after work.
Yeah. So if you have a very old Teflon pan with a scratch coating, I would suggest you throw it away and buy a new Teflon pan if you like Teflon. The newer Teflon pans, since there's an ingredient that there is no longer allowed to be used. So if you have a pan that's more than 15 years old or so, I forget the date, I would just throw it out if it's scratched. So when you cook with cast iron, the worst thing that happens is some iron dissolves in it, and it turns out your body needs iron. So it's actually beneficial, and you can increase your iron, your iron hemoglobin or whatever it is by eating on cast iron. And especially when you cook something like spaghetti sauce, you're actually going to dissolve quite a lot of that iron into your spaghetti sauce.
West 127th Street.
Gosh, I said something, it made Siri launch a map.
Proceed to North River Road, then turn left.
So while Janet's fixing her phone, Jane has a comment about cast iron and whether it should be machined. And I have a couple of really, really nice cast iron pans. I forget who made them, but they're certainly machined. And the surface is much, much better than as cast. And of course they have to be seasoned. And I've found that if you pay attention to your seasoning, you dry the pan after you wash it immediately, I never have a problem with rust. And so, yeah, the S-cast surface is not what you would use for that. You definitely have to clean it up with some kind of machining. Japanese swords. So the Japanese swords, they have a layered approach where they kind of try to smash those layers together. And I don't remember if they actually quench and temper those or not. I think they probably do, but I can't remember for sure. Tempered steel ice scraper. I received a brass bladed ice scraper and was told it was brass because it was softer than brass. Ward Christensen.
Oh, maybe for the windshield he's talking about.
Yeah, so the scraper that I showed was for sidewalk, for getting like 2 inches of ice off your sidewalk in Houghton.
Because you don't really want to scratch your windshield when you're, and that's why most of those windshield wipe scrapers are made out of a polymer, because polymers can't scratch glass. Or most polymers can't scratch glass.
So Harry Jones says one of the stars in History Channel's Mountain Man makes a living in the Ozarks making knives using his homemade forge and other gear. He's also mined iron from a cave near his property. That's awesome. With a high hardness, does that make it brittle? Stephen Conrad said, excellent question. And you probably have some experience in this, that in general, for all high performance metals, if something gets stronger or harder, it also gets more brittle. And so one of the reasons that New West knives can get away with $400 for a chef knife is because it's made out of that powder metallurgy crucible steel. And they've developed that alloy over the number of years, and the molybdenum apparently adds toughness to it. And so that's one reason why it's such a good knife steel. They're not the only ones that use that steel for their high quality knives. And it's been 30 or 40 years of alloy development, making different materials to have high hardness and high toughness. Ballistic applications, absolutely. All high performance steels are quenched and tempered. So absolutely. So high hard content to make the steel more brittle. Yes, it does. Yep. What kind of knife for filleting fish? That's a good question. My son had a knife, and you usually want them to be relatively thin and relatively flexible. And they don't usually have to be that sharp because you want them to be able to bend around the bone and things like that. So it's typically, I would guess, a ferritic or an austenitic stainless steel, very thin and also very not brittle at all. You don't, because it's got a bend, right, when you're pushing it around the meat of the fish. What role does AI or supercomputing have in developing new metals with amazing characteristics? An incredible role. And it's more and more important. And it's one reason why our department has been actually getting a lot of funding to study metals after people told us 30 years ago that metals research was dead. And the reason is because there are so many compositions that haven't been explored. For example, the nickel-based alloys that I work on for jet engines typically have 12 or 13 elements in them for different reasons. And there's no way you can know how all that is going to have an effect on the microstructure and the performance. So AI, machine learning, and all that stuff is very, very important in materials research right now. Are knives typically the same hardness throughout, or do they sometimes have different temper in some regions? I think they're usually throughout. I think they're hardened throughout because you basically put them in the furnace and then you quench them, and so they end up all martensite, and then they temper at the same time. So unless there was something really unusual in the tang or something, then I think that they would have uniform properties throughout. That's probably not the case for the Damascus steels, though, because the manufacturing process there. Ceramic knives, they're great. They can chip, though. They have no ductility and no fracture toughness, and so you have to be careful with them. But ceramic knives, they're very, very sharp, and as long as you're careful with them, they can be a good tool in your drawer. But they'll chip, and that sharp edge is very thin at the edge, and if you do anything to it sideways, it could be bad. Best steel for a pocket knife. It depends on how much money you want to spend. You can buy a stainless steel pocket knife for $18. It's not bad for everyday use as long as you want to sharpen it every once in a while. My son Brian, who I'm visiting right now at the Pacific Northwest National Laboratory, is a knife fiend. And he's in 8th grade. He started buying $350 Benchmade and Spyderco pocket knives. And some are S10, some are the 35V alloy that I think the New West knives are. And so basically, it really depends on how much money you want to spend and what you're going to do with it. You know, if you're going to be chopping things out in the woods on a camping trip, then you want to have something that's a little bit less hard so that it's a little bit less brittle. But yeah, they and even 440C is not bad for a pocket knife. That's a relatively inexpensive steel. You can also get cheaper ones that aren't even hardened, and they're not going to be so good. Good quality knife set. What steel should I look for? There's 4 or 5 powder metallurgy steels that are out there, and the Wusthof ones that I like are not powder metallurgy. They're regular ingot metallurgy, so they're forged, they're cast and forged, and they work fine. Once again, the harder they are, the longer they'll hold their edge, but the harder they're going to be to sharpen. Damascus steel, it's like a layered structure. It's like they take thin layers and they forge it and pound it together, so it kind of welds the layers together. That's why it has that really nice pattern to it. It's like a linear pattern that you see, and they basically make it layer by layer, and then I think they austenize it and quench it. Yes, I am familiar with Park River Knives in Escanaba. I am familiar with them. They make good knives, and the other thing that I should say is that if you are willing to take good care of a knife, you can get incredible performance out of tool steel knives. So, for example, D2 is an excellent knife steel as long as you don't let it get completely wet and maybe oil it once in a while. That's an excellent knife steel. And even 1095. I have a 1095 steel knife. I think it might be from that place in Escanaba, actually. And it's just 0.95 carbon and no chrome. And as long as you keep it dry, it's an excellent knife. So you don't have to spend $450 on a knife if you're willing to take care of it. 440C is magnetic. It absolutely is, because it is it's body center cubic iron with iron carbide. No, 440C is magnetic. Cheap cast iron and expensive cast iron. Tennessee and China. I think that's the difference. I'm not, cast iron's not my area, but yeah, I think it's manufacturing quality and where it's made. Best stainless steel for a beer brewing pot, that's going to be an austenitic stainless steel. So you're going to want 304 or 316 probably. Those are the food grade stainless steels, or the austenitic ones. So I would certainly look into that. Quenching in water versus quenching in oil. The difference is the cooling rate. Water is quicker, and oil can be tailored. So there's different kinds of oil will have different cooling rates because they have different thermal conductivity. And so the problem with quenching in water is sometimes you'll crack the thing when you quench it. So if it doesn't have good thermal shock resistance, some tool steels cannot be quenched in water because they'll crack. So then you got to go to oil.
I did not know that. You said the first thing I did not know.
Okay. Cast iron, they don't rust. Yeah, you're right. And it is nice on gas. I have a propane stove and I have cast iron in there. I love cooking on that thing.
Me too.
If you've heard understable for hockey skate blades and ice runner blades to chip or corrode, what is optimal for these? So that's an interesting question, because like Janet introduced me, I play hockey and I have a pair of $950 goalie skates. And they are very, very similar to the New West guys' knife steel. They're powder metallurgy. They're not as hard and they're not as expensive as that, but they're powder metallurgy, quenched and tempered steel. And I can't remember, I think it's a trade name that Bauer has. But yeah, very, very similar to knife blades. And you don't want it as hard because, like you said, you don't want it to chip, but they work really well. Hockey stick applications. No, it's steels are too heavy for hockey sticks. There was a time when hockey stick shafts were made out of aluminum, out of hollow aluminum, but they don't do that anymore because the composite but doesn't vibrate as much mainly, and it's also higher performance. Hydrogen embrittlement prevented. I don't know that I have time to get into that one. Golf clubs. Yeah. So the heads, the impact heads on the golf clubs are all quenched and tempered steel. Absolutely. And you want the golf club manufacturers have their own proprietary steels to make them to make you want to spend $4,000 on a set of clubs. What can cause a hot spot on my stainless steel pan? That's a good question. I don't know if I can answer that one. I don't know, Janet, you got any ideas?
Well, just again, the ones that are stainless steel solid all the way through are not as great for cooking as the ones that have a copper bottom, because the copper spreads the heat more. The copper conducts better than stainless steel, and so They're not as pretty though. You can put them in the dishwasher, but I'm not a big fan of polishing my copper bottom pans, and I still have some, but I don't keep them beautiful. I just put them in the dishwasher.
Best cutting board, wood or polymer? Janet, do you want to take that one?
Oh, I would say it depends. For meat, I use polymer, and that way I can throw it in the dishwasher and be sure that all the germs are gone.
Yeah.
And for vegetables and stuff, I prefer wood, and I don't put it in the dishwasher. And often I'm just brushing it off and not even soaking it or washing it at all, because vegetables are not very germy. So that's my answer. What's your answer, Walt?
Yeah, I worry about wood with organic material getting in there and being trouble. And so you can get pretty expensive polymer cutting boards at like Williams-Sonoma and those kind of places. And it's not just the cheap polyethylene, and it works pretty well. That's what I prefer to cut on. Okay, road milling asphalt cutting tools, 15V37. So that's our as quenched to Rockwell C54, and the shanks are induction tempered to 35 to 40 to maximize strength. That's interesting. Yeah. So a lot of times in applications like that, you need a much higher fracture toughness and much more ductility than you need in a knife edge. So you can't make it Rockwell C65 because it'll just shatter. So that's good. So like I said, you don't always want to have the hardest possible steel. Do they have tungsten carbide tips? I'm not aware of any kitchen knives or pocket knives that use carbide tips. No. Carbide tips is typically used on a drill bit or a saw blade, and it's brazed on, and it's pretty thick, and it's probably not what you would want on a knife. Steel guitar strings made from, I don't know for sure. I would guess they've got to be some kind of stainless because they're not rusting all the time, but I don't know that I can answer that one.
I don't know. Well, that was a lot of questions. I think we've answered 32. I wasn't tracking fast enough. You're the fastest answer of questions I've ever seen. Do you want to take another quick scan through?
Well, somebody said that they do have tungsten carbide tips, so maybe they do, like on the very, very tip, but not on the edge of the blade, I wouldn't think. So if somebody put a link in the chat, if you want to click on it, on the forging the Japanese swords with the Damascus steel process, I think they call it. And yeah, that's interesting. Thanks, Randy. I appreciate the compliment. So.
All right. Well, we're coming up on the hour. This is the time at which I just thank everybody for joining us. And so I'm joining you this week from Chicago, Illinois, where I'm visiting family and also meeting some Michigan Tech Huskies. Walt, where are you again?
I'm in Richland, Washington at Pacific Northwest National Lab.
Yep, and he's visiting his family and hopefully having some good restaurant meals and fine wine. And so thank you everyone for joining us for Husky Bites. None of us were in Houghton except for some of the people in the audience.
I did forget to mention that we did stop in Seattle and watch a hockey game on Saturday too.
Oh,
Seattle Kraken and Pittsburgh Penguins.
That sounds like a whole bunch of fun.
It was fun.
Well, thank you everyone for joining us. We will see you next week. I will be back in Houghton, and so will Walt, but we have 3 more Husky Bites, and then the last one wraps up the Monday of Thanksgiving week. And so I will see you next week. Thank you, Dr. Walt Milligan from Material Science and Engineering at Michigan Tech.
Stopping by, folks.
Yeah.
Bye.
Good night.